All right. So let's continue where we left off on Friday. So on Friday, we introduced the notion of a vector space and vectors, and we defined some of the basics, the directional vectors, component vectors, and then we talked about generalities of size and magnitude. We will talk about that again. And then we talked about specifically the algebraic operations of scalar multiplication and addition. So let's go ahead and start there and talk a little bit more about the geometry. So we've mentioned how vectors are drawn by arrows at the origin. So if we have two vectors, u and v, what are we doing when we add two vectors? What you want to do is draw either vector, pick one first. So if we're doing u plus v, we can draw u first. And then what you want to do is translate v to put the starting point now at the tip of vector u, and then draw the corresponding vector for v. Then if we now draw a point or a vector from the origin to the tip of this translated v, then that vector there is u plus v. So for example, if we are going to draw u is equal to, here, I'm sorry, let's write it as column vectors. Let's say 1, 0, and v is equal to 1, 1. Algebraically, we should get u plus v is 2, 1. So we're just adding in components. Graphically, if we want to draw an accurate graph for this, so our u is going to be along the x-axis. So u is the component vector along the direction of x. V points to 1, 1. Whereas the point 2, 1 will be over 2 and up 1. And we can see now that if we follow our geometry and if we translate v starting from the tip of u, then the resulting vector we draw from the origin gives us 2, 1. In terms of scalar multiplication, so for a real number t and some vector v of dimension n, if t is positive or 0, we scale or stretch v by that factor. So if we have a vector v, and let's say we pick our t is equal to 2, then we are going to scale the vector, and 2v is just going to be a vector in the same direction, just twice as long. If t is negative, then the vector flips. And scales. So if here's our vector v, then a vector drawn as such, this might be something like -3 times v. And of course, the scalar can be any real number. So if the scalar is a fraction like 1/2, it would be half the length. If the scalar is 0, then we simply just get the 0 vector.
Is the -3v, is that only the red, or is it the whole length again?
Just red. So all of our vectors are starting at the origin. Okay, so the book talks a little bit more about distance and length. We mentioned this formula on Friday. Let's talk a little bit more, go a little bit more in depth. We did not have a lot of time on Friday. It was kind of a short lecture, so I just wanted to introduce a lot of the different concepts. And then so now we've got back to our normal schedule. We can go into a little bit more depth. So in terms of distance and length, for a point P and a point Q, in Rn. So points, we want to consider just as points. Vectors, when we talk about Rn and define vectors in Rn, we think of the vector space Rn. Points, we typically just think of an n-dimensional Euclidean space. But we often define the distance between P and Q by d of P and Q. And what do we want to do? We want to add up the difference of the coordinates square them all, add them up, and then compute the square root. So this is our nice Euclidean geometry, except now expanded into higher dimensions. So just like the Pythagorean theorem in two dimensions, a squared plus b squared equals c squared, we are now looking at really the legs of a triangle. So it's going to be hard to draw in higher dimensions, but for example, if we have a vector, it's going to have some x component. So this might be the difference between a point and an origin. And then it's going to have its change in y, its change in x, and then the vertical component, the change in z. And so it'll give us x squared plus y squared plus z squared. The vector we often denote it either as PQ, or we often define, say, a vector v or a vector x as the difference between the 2 points, q minus p or p minus q. So you do want to mind the direction and the subtraction. So if we do q minus p, we call it the direction vector. Or directional vector. From P to Q. Meaning, if we have some point P and some point Q, we think of this vector now starting from P and then going towards Q. So one thing to note, it is going to be a little weird because we're going to see some examples where we have these directional vectors that are not starting at the origin. So in general, what you really want to think of, we have defined vectors as always starting at the origin, but really what's going on, so here, this is a two-dimensional plane. And what you want to think about is almost having a plane over top of itself, like R2. We really are working with two copies of R2. The base copy is just the set of points, and then over top of that is going to be our set of vectors. So usually when we're working in a geometric space, we have some sort of point or reference point that we care about. So in this case, if we have points P and Q, and we want the directional vector starting from P, ending at Q, geometrically, well, we want the vectors to start at P. So what's going on here, which is often hidden from textbooks, is that there's almost an extra copy of R2 over top of the plane. And so really what we kind of have is a hidden copy of R2 where the origin, our reference point, we want to think of ourselves sitting at P. And now the vector or the direction we would need to walk from P to get to Q is given by our directional vector. So it's almost like we shift the origin to P, and that is our reference point. Whereas the absolute origin, you can kind of think of as an absolute reference point, but then the point we are standing at, our reference frame, would be looking like our origin is at P. And so, of course, from our distance formula, we have our magnitude. Or we often call it the length of a vector. So once again, our formula, if we have a vector given with components x1 to xn, then the length is written with 2 bars, kind of like an absolute value. And again, that's just going to be the sum of all of the components squared, and then take a square root. So a unit vector is just a vector whose magnitude is 1. So some examples. Find the length of the vector v Let's do 1, -3, 2, and 1. So finding the length, we would just do v, norm v, is equal to, and then it's just the sum of these squares, so 1 squared plus, mind all the negatives will end up being squared away. So when we're computing the norm, even if the individual component is negative, that negative sign isn't going to change or isn't going to affect the length. Sorry, 2 squared plus 1 squared. And then we want to square root everything, which is oftentimes easier just written as the 1/2 power. And so what are we going to get? 1 plus 9 plus 4 plus 1 to the 1/2. And so we've got square root of 15. Likewise, find the length of let's say v is equal to, sometimes the book writes vectors as row vectors transpose. So we could write it as something like square root of 3 over 2 and 1/2. And then they'll write a transpose here. So remember, transpose, all it does is change rows to columns. So anything in a position 1, 1, flip the row and column is going to stay in 1, 1. In position 1, 2, that would go to position 2, 1. So this is the same as writing a column vector with the same components. Length of v is going to be square root of 3 over 2 squared plus 1/2 squared equals 1. So v is a unit vector. Couple properties about scalar multiplication, addition, and norms that we are learning here. It's going to be a little bit out of order. Let's introduce the first property. Scalar multiplication is fairly easy. So
sorry, can I interrupt real fast?
Yeah, sorry.
On the last example, did we not square root?
I did forget that. Of course, square root of 1 is still 1.
Yeah, just making sure.
Yeah, my brain was getting ahead of myself. So, of course, I cooked up those numbers. I knew the answer was going to be 1. So thank you for that. I did forget that square root, though. So some properties for any scalar and a vector v. If we scale the vector first, and then compute the norm, that's going to be the same as just taking the magnitude of that scalar or the length of that scalar. Again, might be mindful that scalar could be negative, so it could flip the direction. But if we flip the direction, really all that matters in terms of the length, well, flipping the direction isn't going to change the length. It's really the magnitude of the scalar that will affect the ultimate length. So the length of the resulting vector is just going to be the absolute value of that scalar times what the magnitude would have been of the unscaled vector. Big examples for this. So let's say find a unit vector in the direction of v, which is going to be 1, -3, and 4. So direction, we will kind of have to talk a little bit more about once we get into the dot product. But for now, since we understand that scalar multiplication of a vector doesn't change the direction, right? It just scales that vector. What we want to do is scale this vector so that it has unit length. So our first step is to actually compute the length of the vector we are given. And since we know that scaling a vector won't change the direction and it will affect the magnitude simply by the norm of that scalar, all we have to do is multiply by the reciprocal of the magnitude. So let's define W equal to 1 over the square root of 26 times V. Then the norm of W is going to be the norm. So let's write it as the norm of 1 over square root of 26, -3 over square root of 26, and 4 over square root of 26. Which will give us the sum of each of the components squared all square root and as we see, sum of the numerators is going to be exactly the denominator, and so we'll just get 1. In terms of vector addition and norms, we get what's called the triangle inequality. So we won't be able to prove it at the moment. We can prove it by the end of class. So let's just state it here. briefly, we'll just say that the norm of x plus y, so if I'm adding two vectors, then, oops, sorry, that should be a less than or equal to the length of x plus the length of y. We don't have the algebraic tools quite yet to prove this. Geometrically, we can get a little bit of an intuition for it. So if we have a vector x and then some other vector y, our x plus y since it is drawn from the origin to the end of y, where we've taken y and translated it to the tip of x, well, you should also get the sense that if this vector is x plus y, by the properties of addition, it's also going to be y plus x. So we have this parallelogram that we can draw, and we see that our vector x plus y is going to be the diagonal. So really what it's doing is comparing the diagonal of a parallelogram to the length of its sides. And more so, hopefully someone somewhere along the lines taught you in geometry class that if we have three numbers, when can those three numbers be the side lengths of a triangle? And the condition of that is that the sum of any two of the numbers has to be bigger than the third. So it's a similar concept that's going on here. Primarily, you can also think about it in terms of distance. If I were to walk from the origin to the tip of x plus y, what is the shortest distance? Well, the shortest distance is going to be the straight line or the vector joining those 2 points. Whereas if I walk along x first and then walk along y, we're going to be walking a further distance. So the distance walking along x plus the distance walking along y is going to be bigger than the distance had we walked in a straight line to that destination. Once we introduce the dot product, we'll be able to talk about a more rigorous proof. We will need the Cauchy-Schwarz inequality first, though. Any questions on any of that? Okay, so to get into a little bit more geometry, let's talk about lines and planes. And again, we kind of introduced these topics when we were looking for solutions of linear equations. We didn't have a solid interpretation of them in terms of some of these building blocks we're now working with in terms of vector spaces and vectors. So let's formalize a little bit better our parametric equations and equations of lines in Rn. So a line is a one-dimensional vector space in Rn. These definitions are going to be a little bit different, and I'm going to use some slightly different words than what you're used to. Don't worry, though, we're not going to get too theoretic with it. So when I say a one-dimensional vector space, remember from Friday that a vector space always contains the origin. So sometimes we combine these two definitions, and we often describe things, we want to describe vector spaces, so to speak, or equivalent geometric objects as to whatever dimensional vector spaces, whether it's a one-dimensional line or a two-dimensional plane. Sometimes those don't pass through the origin, or sometimes we want to think of the origin shifted from a different reference point. So we simply tag on the word affine. So an affine line is a line translated from the origin. From this class, the words line and affine line, we can essentially mold into one. So we can kind of consider lines all as affine lines. So the defining information is going to be a point. This is going to be essentially thinking of that as like the starting point, or wherever we are translating, wherever we are moving our reference frame to, and a direction. So this is the minimal geometric information. If you have a point, starting point, and then a direction of travel, namely a vector, then that information can define a line. So we often parameterize lines in such a way. So let's describe our line as y of t is equal to x plus t times v. So this x, we can call our initial point, or vector, since we do want to move a little bit away from the notion of points, and our initial vector, or you can talk about the initial position vector. And then this v here is going to be known as our directional vector. So this is the direction we are traveling. So if we were to write this out a little bit more in terms of our components, right, we've just got our x1 to xn plus t times v1 to vn. So if we were to properly define a line or a one-dimensional vector space, we would need it to pass through the origin, meaning that this starting point would have to be 0, or that the starting point or our initial position vector is going to be some sort of scalar multiple of our directional vector. So from this, we can deduce our parametric equations. So we've got, and let's list our dependent variables here. Our equation had y was equal to x vector plus t times our directional vector. And so what do we get for our parametric equations? We get a set of equations where in the ith component, our yi, our dependent variable, is going to be whatever the initial position was for that coordinate plus t times the directional component. So for example, in 3 dimensions, be careful again with the variables we are using. Sometimes we have x's as our independent variables. Sometimes it's an initial position, and I'm using here y as our dependent variables. Sometimes we have x, y, and z for our position variables, or for all of our dependent variables. So find parametric equations for the line between, let's say p is equal to 1, -1, 0, and q is equal to -2, 0, 1. So how do we do this? Our directional vector is going to be the difference between p and q, and we just take the difference component wise. So if I'm doing q minus p, mind the order, make sure you're just consistent on the order. For a general line, it doesn't matter which direction you travel along the line. Since we are taking scalar multiples, you can include that scalar to being positive or negative. But if we do need a specification, q minus p, we are going to be pointing in the direction from p to q, ending minus the start. So we'll have a -3. We will have a +1, and then 1 minus 0 gives us a 1 in our z component. And then so our line, we can write either as a function, or we often write, let's use x vector as a function of t, is going to be our initial position, some starting point, which you can pick any point we have on the line as a starting point. Let's go ahead and pick p, since I chose the directional vector from p going to q. Again, it doesn't matter. Both will work and both will ultimately give us the same line. But to illustrate this a little bit, let's pick our starting vector as p. And then our equation will be that p, now as a vector, as a positional vector, plus t times our directional vector. And so if we wanted to write this out in terms of the coordinates, again, because this is 3 dimensions, we often use our x, y, and z for the variables of the directions of our coordinate directions. And t is our independent variable. Which is going to give us the set of parametric equations. X of t is 1 minus 3t. Y of t is -1 plus t. And z of t is just t. So as a check, we can check what is going to happen when t is equal to 1. So this kind of ties back with the specifics of how I set it up. The directional vector, when we are scalar multiplying it, so when t is equal to 1, you can kind of think of t as time. This is why we use t for our independent variable often with parametrics. We want to think of us starting at this position, 1 minus 1, 0. And then as time progresses, we are walking in the direction of our directional vector. So after 1 second, let's say, we have walked 1 unit length in the direction of our directional vector. Meaning if we started at the point 1 minus 1, 0, walked for 1 unit of time with the direction and speed determined by our directional vector, then we should end up at another point on the line, and specifically the point we ended up at, we see is Q. So since the directional vector represents both the direction and the length, the distance between P and Q, if I walk 1 unit of time going in that direction, starting from P, we will end up at Q. So let's see, we've got about 45 minutes. Let's do this for 1 dimensions. So we did leave a problem hanging. So from Friday, we talked about the formal definition of a vector space, right? So remember, a vector space is a collection of objects that we call vectors in Rn, such that we can add and we can scalar multiply. So loosely, vector space is going to be a set of objects in Rn. And then let's just write it out. So such that, and let's call this a vector space V, for any 2 vectors in the vector space, and any scalar, we have closure under addition, meaning if I add any 2 elements of this set, we still get a new element that is in the set. And if we scalar multiply any element in our set, we get a new element within that set. And so the example we started with, we can formalize a little bit differently now. So show that the line through the origin with direction v equal to 1, 1 defines a vector space. And you can generalize this argument to show that any line through the origin is going to be a vector space. So our line call y of t, is just going to be our point. And since we're going through the origin, we can have our starting point simply as 0 plus t times our vector v. In other words, y of t is just going to be tv, or t times 1, 1. So quick proof of this. So let's pick different letters. Let's say U and W on our line y of t. So by the definition of what the line is, there exists real numbers, s and t, such that u, so if u is on the line, it has to be some scalar multiple of 1, 1. And likewise, w also has to be some scalar multiple of 1, 1. And so what do we want to check? Since our choices for u and w were arbitrary, right, with arbitrary constants, all we want to check is that properties 1 and 2 hold. Namely, if I take u plus w, by the definition, how they were constructed by our properties of this line, this is going to be s times 1, 1 plus t times 1, 1. And by our algebraic properties of addition and scalar multiplication, primarily the distribution property, I can write this as s plus t quantity times our vector 1, 1. And since s plus t, well, that's just a real number. I can add two numbers and get a new real number, which we can call by some different constant, c. And so again, we simply get another scalar multiple of 1, 1, which by definition is going to be on the line. Likewise, for any other constants, if we take that constant times u, well, that's just going to give us k times s times 1, 1. And by our associative property, I can multiply the k and the s and again get new constants. And since this is just going to be a constant multiple of 1, 1, that is the definition of all of the elements on our line, which means this element in particular will be on the line. So essentially what we've shown is that for any two vectors that are on this line, we can add the two vectors and we can scalar multiply. So this line is a vector space. Any questions on that? So last thing we might want to do with these parameterizations of lines is now that we've seen how to parameterize lines, we can find points in between lines, outside of lines, and answer questions like, let's say, find the point between, let's see, that lines. Let's say 1/5 of the way between, let's say P is 1, 0, 1, 0, and Q is 0, -1, -1, 0. So we had a question in chat real quick. How can we differentiate between a vector space and a non-vector space visually, graphically? So vector spaces are always linear objects through the origin. So it's going to be hard to visualize on higher dimensions. But in 2 dimensions, your vector spaces are either the entire plane itself, lines through the origin, or the 0 vector. So this was kind of related to homework 1, but we didn't have the formal introduction of vector spaces yet. You guys saw a lot of these intersections of planes and lines and trying to match equations. So in R2, there's essentially 3 possibilities for vector spaces. Either the whole plane, or we just saw one example of lines through the origin, but any line through the origin will give us a vector space. I'm running out of colors. Lines through the origin. And then the last option is the 0 vector space. It's only one point. One point, we should say one vector. Namely, it consists only of the 0 vector. So this is a 0-dimensional. So 0D. These are all 1-dimensional vector spaces. And then in R2, the entire plane is a 2D vector space. As soon as we start looking at vector spaces in 3 dimensions, then we're going to have more. So in R3, you kind of want to generalize that same process. We get the whole space. Oop, I'm dropping my pen here. So all of a 3-dimensional space. This is going to be our 3-dimensional vector space. Our 2-dimensional vector space is essentially going to be like the previous example. We only had one 2-dimensional vector space in our previous example. It was just the plane. Well, now what do we want to look for? We want to look for planes, but now planes sitting within 3-dimensional space. So a two-dimensional vector space within a three-dimensional vector space is going to be a plane. So, well, a two-dimensional vector space in any dimension vector space bigger than 2 is going to be a plane. And it gets a little more complicated now, because now we can have things like the XY plane, but then we can twist and orient and rotate in a lot of complicated ways. So it's going to be messy if I start to draw too many of them. Let's draw one perpendicular to that, but at a diagonal. So one that goes like up and down. And cuts through that. So our red plane might be like the XY plane. And then the green plane is a vertical plane that follows the line x equals y. But again, a vector space, all of these vector spaces have to go through the origin. So 2D are going to be planes through the origin, and then 1D and 0D are essentially going to be the same. We just have more degrees of freedom, so to speak, for one-dimensional. We're still going to have lines through the origin. And then, of course, the 0D is just always going to be a point, always going to be the base point. So lines through the origin. Lines are even harder to draw with the right perspective. But as long as they go through the origin, whether it's in, out, left, right, however you want to spin these lines, all those will define a one-dimensional vector space. And you can generalize this to higher dimensions. Just going to be hard to visualize. In four-dimensional space, we're going to have different three-dimensional subspaces. Whereas in 3 dimensions, there's only one three-dimensional vector space. As soon as we increase the dimensions, well, now I can have multiple different three-dimensional vector spaces. We have even more two-dimensional vector spaces in a four-dimensional vector space. And we'll start to develop more tools to work with these as we keep going. We'll still have a week or two. Once we start talking about transformations, we'll start to tie in matrices as well, and how we can use matrices to model these vector spaces. Okay, so back to some problem solving. Hopefully, if you guys had Calc 3, everyone kind of understands how to find the midpoint between 2 points. So just as a refresher, the midpoint, we just average all the coordinates. And that actually goes for however many points you have. If you have 3 different points, like a triangle, and you have 3 points, and you want to find the average or the midpoint of 3 of the triangle of the 3 points, you just average all the coordinates. So of course, 2 points only define a line, and then the midpoint, we would just take 1 plus 0 divided by a half, 0 plus -1. So in midpoints, the signs matter. Of course, 1 and -1 is 0, 0 and 0, still 0. So the midpoint's pretty easy. We can have this nice formula for it. How would we find something that is a fifth of the way between the 2 points? Well, if you're really clever and you understand a little bit of maybe probability, you might think of it as simply a weighted average of the coordinates. That would actually get it to you. But let's take our geometric approach now. So we can find the line between P and Q as 1, 0, 1, 0. Let's go ahead and start at P again. And I guess we should specify, find the point that lies 1/5 of the way between P and Q. And so maybe we should be more specific, from P to Q. So we have a defined starting point. We want to start at P and walk 1/5 of the way from P to Q. Yeah, it looks like someone was asking about that in chat just now. So we'll start at P, and then how do we walk towards Q? We need to find our directional vector. So let's just do a little scratch work on the side here, since these aren't terribly hard to compute. We want to do ending minus the start. So Q minus P. So we'll have a -1, a -1. Q minus P here will give us -2, and then 0 in that last coordinate. Do we want to change that? I just realized I put zeros in that last coordinate. Let's just keep it. It's not going to matter. Since both of those coordinates are 0 in the last coordinate doesn't really matter. It's always going to be 0. It'll save us a little computations. And so now, as we saw with our previous example, this is our directional vector, and it's kind of scaled to time. So every unit time that ticks by, we're going to be walking in the direction of this vector and its length. So 1 unit time that ticks, we are walking the length of this vector in the direction of the vector. So when t is equal to 1, we can go through the computation again, and you should see that we will end up at Q. So we don't want to end up at Q, we just want to end up 1/5 of the way there. So we just want to pick t is 1/5. Okay, and then so we compute that. So I was reading chat a little bit. Someone mentioned -1 instead of -2. Did I do any of the computations wrong real quick? So always make sure we're doing Q minus P. So 0 minus 1 gives us that -1. -1 minus 0 gives us -1. -1 minus 1 gives us -2. 0 minus 0 gives us 0. So I think I did it right. And of course, we can check if t is equal to 1. We will have 1 plus 1 gives us 0. 0 minus 1 gives us that -1. 1 minus 2 gives us this -1. And then 0 and 0 still gives us 0. Yeah. Yeah, mind the directions, mind the minus signs. These are always the biggest mistakes in these types of problems, which I'm fine with. If that's the only mistakes you guys are making are these small little minus sign errors, everyone will do perfectly fine in this course. Because I make those too. Everybody does. Okay, so let's just compute this out. 1/5. So we've got 1 minus 1/5, so 4/5. And then we've got 0 minus 1/5, so -1/5. And then 1 minus 2/5, so -3/5, and then 0. So nothing terrible there. Hopefully lines are pretty easy. If you've had Calc 3, they should be very easy. If you haven't had Calc 3, this is kind of a beginning topic that we talk about in Calc 3. So it's not really deep into theory or anything like that. Fairly basic still at the moment. Okay, so let's talk briefly about planes. And we'll maybe return the planes and touch up with specifics of planes in R3 have a special property that they can be defined by their normal vector. So this is going to be different from the book. So just like lines, our definition is going to look very similar. So a plane in Rn is a two-dimensional vector space. And again, because we are specifying it as a vector space, that means it has to go through the origin. Every vector space contains the origin, contains 0, 0, 0. Geometrically, it is defined by a pair of directional vectors and we should specifically say non-zero. I didn't specify that in the last example either, but anytime we're considering a directional vector, directional vectors are specifically non-zero. We don't really consider zero as walking in a direction of going nowhere. Pair of directional vectors, let's call them u and v. And then we got to be a little more careful such that they're not scalar multiples of each other. So we've seen that scalar multiples of each other would define essentially the same direction. A scalar multiple of a vector doesn't change the direction of the vector. So we need two unique vectors in some sense. They have to be separate directions in order to define a plane. So parametrically, we might define something like our y. It's now a two-parameter family of solutions. So we saw some examples when we're looking for these solutions of systems of linear equations. When you find infinity solutions, and we had a one-parameter family of solutions, essentially what that meant was that the vector space, or the solution of our system of linear equations, was a vector space defined by a given line. As we just saw, our lines needed one free parameter to define a line. If we have a two-parameter family of solutions, this defines a plane, which we simply write as S times V plus T times W. So for example, suppose we have directional vectors u is equal to, let's just do 3 dimensions to keep our computations a little shorter. Let's say 1, 0, 1, and v is equal to, let's say 0, minus 2, minus 1. And so our question might be something like, does the point let's do a couple of them here. are the points on the plane defined by u and v. And so let's say A. Let's see. Let's do P is equal to, let's keep it as a vector and keep it considering it as a position vector. Let's do something like 3 minus 2 and 2. And then let's do B. Let's do 2 minus 4 and 3. Let's call this guy Q. So we want to check, can we get to these points by walking along the plane that is defined by these two vectors? So in some sense, what you kind of want to do, as I was trying to draw, I don't know if I'd be able to draw this plane. What you kind of want to think of as starting at the origin, whatever S is, that's the number of multiples we're going to walk along our V vector. So I've changed the notation around a little bit. Let me redefine this. Sorry, I was using U and V. Someone should have said, where the heck did W come from? Let's have it as S times U plus T times V. So if we're starting at the origin, all you got to do is walk S times in the direction of U. So take U and line it up S number of times, walk in that direction. And then from that point, line up T copies of V and then walk in that direction. Wherever you end up is a point on the plane. And all such combinations define all of the points, places you can get to that are on this plane by walking along our directional vectors. So what we want to do is we want to solve now a system of equations. We have this point 3 minus 2, 2. If we want it to be on the plane, it should be some combination of U and V. And so what we would have to do is check, can we find these scalars? So we will have S times 101 plus T times 0 minus 2 minus 1. And now we have a set of equations. So the top equation is going to say 3 is equal to S plus 0, 0t, minus 2 is equal to 0s, minus 2t. And then our last coordinate, we've got 2 is equal to s minus t.
Can you put the other page back on for just a second?
Sure.
The very bottom. Thank you.
So this is our vector equation, and our vector equation defines a system of equations, and now we are solving for S and T. Nicely enough, we don't have to use any of the techniques. So any of the techniques we were learning in chapter 1, we could apply here now to try to solve for our constants S and T. Luckily, we've got some zeros in there. So this equation implies our S is 3. This equation implies T is 1. And what do we want to check? is this consistent? So if S is 3 and T is 1, do we get a valid equation? It works. So we have a consistent solution with S equals 3 and T equals 1. And so our solution to A is, yes, P is equal to 3 times U plus V. We want to do something similar for B. So our Q was 2 minus 4, 3. And again, we're looking for constants S and T. Oops, sorry for being off screen there. So this was the point in question. We want to know, is this on the plane? And if it is on the plane, it should be able to be written as a linear combination by walking S units of U and T units of V and arriving at our point. So this gives us a system of linear equations. 2 is equal to S plus 0. Minus 4 is equal to 0 minus 2t. And then 3 is equal to S minus t. Again, we could use our matrix systems if this were a more complicated set of equations. But since we have it essentially solved for our variables, S is going to be 2 in this first equation. Our second equation dictates that T is also 2. But then when we check our third equation, this is going to say 3 is equal to 2 minus 2, which equals 0. So that wouldn't work. So since the first two equations dictated that S had to be 2 and T had to be 3, or excuse me, S had to be 2 and T had to be 2, we see that if we walk 2 units of U and 2 units of V, that's about as close as we can get. We're never going to hit this actual point. And so since the system is inconsistent, this point Q is not on the plane. So last points to talk about with planes. So our definition, an affine plane so again, this word affine shows up, just means we are looking at a two-dimensional object, a plane, that is translated from the origin. So our parametric equations look something like y of S and t is going to be some sort of starting vector or a translation vector of where we want to think of our origin being shifted. And then from that point, we can walk in 2 directions, either in however many copies of U, or we can walk in however many copies of V, or any combination of those 2. So again, we have 2 directional vectors. And then this, think of it as like a positional vector or a starting vector. So example. So from Calc 3, you guys should have seen equations like z is equal to x squared plus y squared. If you haven't had Calc 3, don't worry too much about it. I don't want to go into the specific details, but maybe we can just kind of draw geometrically what's going on. This is what's known as, I think it's called a paraboloid. So z equals x squared would give us a parabola. So this looks like a parabola that is just rotated. So it's like a parabolic bowl. That is rotated around the origin. So the tangent plane at 1, 1, 2 has directional vectors let's call it u is equal to 1, 0, 2 and v equal to 0, 1, 2. And we want to find the parameterization. So we're given the directional vectors and the starting position. We can essentially just define it as that. Let's see, I don't want to use y because we want to use y as one of the coordinates. Let's just pick another independent variable. Let's actually call it r of s and t is going to be the starting vector 1, 1, 2 plus s times our first directional vector plus t times the second directional vector. And then if we wanted to write these in terms of our coordinate positions and parameterizing each specific coordinate, that's just going to say that our x coordinate as a function of s and t is going to be 1 plus s plus 0t. Y of s and t is going to be 1 plus t. And then our z coordinate is 2 plus 2s plus 2t. So essentially what we're doing, if we were to find the point 1, 1, 2, so here's the point 1, 1, 0, 1, 1, 2 is going to be up here. And what we are doing, so if you haven't had Calc 3, this might be a little unfamiliar, but you can kind of imagine that with this bowl, if you pick a point, instead of having tangent lines to that point, you can define a plane that touches this bowl at that one point. That's essentially what we've done here. So it should be slightly angled up. I don't know if I can draw it really well. So it'd be the tangent plane to this point. And again, what you kind of want to think of, the origin being translated to this point. So if we were now standing at that point, locally on this surface, we could essentially define a coordinate system by these two vectors in two directions we could walk. Namely, if I walk 1 unit in the x direction, we are actually going to go up 2 units in the z direction on this object, on our plane. If I walk 1 unit in the y direction, we would also walk up 2 units in the z direction. Any questions on that? All right, so that is a really good point to stop. We will start tomorrow. Now we'll talk about the dot product. So the dot product is going to be an operation on vectors that gives us a notion of angles. So we can add vectors, we can scalar multiply. We have this notion of direction. But now we want to talk about angles a little bit. And really, what are angles? So we kind of need this notion of a plane, because if we're going to talk about an angle between two vectors, we really want to measure that angle in the plane that is spanned by two such vectors. So you kind of want to think of wherever those vectors, if we are translated, most of the time we are going to be in a plane that's starting at the origin, and you kind of want to think that the two directional vectors we can walk might define a certain angle between them. And so we will find those angles in that plane. Then there's also this notion of projections and scalar multiples, and projecting one vector onto another that we will get from the dot product.